In this video, we introduce the two most powerful tests of convergence: the ratio and root tests. Now let's consider the series A sub n. Furthermore, we're going to say let rho be the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. There are three cases that we consider. First, suppose that rho is less than 1. If this is the case, we may choose a number r such that rho is less than r, which is less than 1. Since the absolute value a sub n plus 1 over a sub n converges to rho, there exists some value big M such that the absolute value of a sub n plus 1 over a sub n is less than r for all n greater than or equal to big M. Thus, if we look at the absolute value a sub m plus 1, this is less than r times the absolute value of a sub m. If we look at the absolute value of a sub m plus 2, this is less than r times the absolute value a sub m plus 1. But that would be less than r squared times the absolute value of a sub m. Looking at absolute value a sub m plus 3, this would be less than r times the absolute value of a sub m plus 2, but that is less than r cubed times the absolute value of a sub m. Right? We can continue in this way. So that in general, what we find is the absolute value of a sub m plus n is less than r to the n times the absolute value of a sub m. Therefore, if we take a look at the series absolute value of a sub n goes from m to infinity. This is equal to this series. Which is now less than series n equals 0 to infinity, r to the n times the absolute value of a sub m. But that a sub m is a constant, right? So we get the absolute value of a sub m times the series n equals 0 to infinity, r to the n. However, the absolute value of r is less than 1. So that means that this series is a convergent geometric series. Well, this means that if you take some number, in this case absolute value of a sub m, and multiply it by r to the n, it converges. So what we can say is that this series converges. And so A sub n, the series A sub n, converges absolutely. Now, so second condition, second possibility, suppose that rho is greater than 1. Then we may choose a value r such that 1 is less than r less than rho. Then there exists some value big M such that the absolute value of a sub n plus 1 over a sub n is greater than r for all n greater than or equal to this value big M. If we argue, as we just did above, except with inequalities reversed, we find the absolute value of a sub m plus n is greater than r to the n times the absolute value of a sub m. But r to the n is going to infinity. This means that the terms absolute value of a sub m plus n do not tend to 0. Which means that the series A sub n diverges. Final case is suppose rho is equal to 1. And what we're going to do is we're going to consider the series n equals 1 to infinity of n squared and the series n equals 1 to infinity of n to the minus 2. Notice that what we have is this series diverges. It's a p series with p equal to negative 2. And this series converges. So if we look at the absolute value of n plus 1 squared over n squared, right, this converges to 1 as n goes to infinity. And if we look at n plus 1 to the minus 2 over n to the minus 2, this becomes the absolute value of n squared over n plus 1 squared. That's also converging to 1 as n approaches infinity. So what this shows that when rho equals 1, both convergence and divergence are possible. We now formally state this. This is the ratio test. Assume that rho equals the limit as n approaches infinity of the absolute value a sub n plus 1 over a sub n exists. If rho is less than 1, then the series a sub n converges absolutely. If rho is greater than 1, then the series a sub n diverges. If rho is 1, then this test is inconclusive. So let's consider the series n equals 1 to infinity, 2 to the n over n factorial. Well, take a look. Limit as n approaches infinity of the absolute value 2 to the n plus 1 over n plus 1 factorial all over 2 to the n over n factorial. Right, so this would be the absolute value, limit as n approaches infinity of the absolute value 2 to the n plus 1 over n plus 1 factorial times n factorial over 2 to the n. Using properties of exponents, 2 to the n plus 1 over 2 to the n is simply 2. N factorial over n plus 1 factorial is just n plus 1. This limit is 0, which is less than 1. So therefore, we can conclude that this series converges. Next, let's consider the series n equals 1 to infinity, n squared over 2 to the n. So absolute value, or limit as n approaches infinity, absolute value of n plus 1 squared over 2 to the n plus 1, all over n squared over 2 to the n. Simplifying this, we get the limit as n approaches infinity, absolute value, n plus 1 squared, all over 2n squared. That limit is a half, which is less than 1. So then this series converges. Now let's consider the series n equals 1 to infinity, negative 1 to the n, times n factorial over 1,000 to the n. Limit as n approaches infinity, the absolute value, negative 1 to the n plus 1, times n plus 1 factorial all over 1,000 to the n plus 1, divided by negative 1 to the n times n factorial all over 1,000 to the n. Simplifying this, limit as n approaches infinity, the absolute value, get -1 times n plus 1 in the numerator, and then all over 1,000 in the denominator. That absolute value is simply this. Right, that limit is infinite, which is indeed larger than 1. So then this series diverges. We will once again consider the series a sub n, except now we're going to say rho is the limit as n approaches infinity, nth root, absolute value of a sub n. The arguments used here are very similar to those used in the ratio test. And so I'm just going to state this next theorem. Which is the root test. We assume that rho, which is the limit as n approaches infinity, the nth root absolute value of a sub n, exists if rho is greater than 1, or I'm sorry, if rho is less than 1, then the series a sub n converges absolutely. If rho is larger than 1, then the series a sub n diverges. And if rho is equal to 1, then the test is inconclusive. We will look at the series n equals 1 to infinity, n over 2n plus 3 raised to the nth power. So we want the limit as n approaches infinity, nth root of the absolute value, n over 2n plus 3 raised to the nth power. I'm sorry, that should be in here. Well, this becomes the limit as n approaches infinity of the nth root, absolute value n over 2n plus 3, and then raised to the nth, which simply becomes the limit as n approaches infinity of n, absolute value of n, over 2n plus 3, which is the limit as n approaches infinity of just n over 2n plus 3, which is 1/2, which is less than 1. So the series n equals 1 to infinity, n over 2n plus 3 to the nth power converges.